Well, I will, before I go on to this, maybe make a comment on something on the continuum of the carbon. We've been working on this thing for a long time, since I guess I can remember 1984. So at least I have some little experience in the chemical engineering, how to produce char and char surface and interfaces. If you look at the continuum that Kurt mentioned, the graphite that you see there with no no oxygen at all. It's and a question that someone asked about what is the temperature and duration effect. We call that in chemical engineering residence time, and temperature, as you all see on the television all the time, is the time and temperature. So if you have, for instance, a slow pyrolysis, or the way we make, for instance, electrodes or something to go in aluminum, smelting, you have a carbon or petroleum coke what has a lot of volatile, but only, you say a lot, but only 12% volatile, and you put it in a kiln at a temperatures of about 1,000 degrees, and then you give it a residence time of about 1 hour, a long time, you evaporate all the volatile in it, and eventually not only volatile, but then you get structure changes. Right? So you change the structure, and then you turn it into a crystalline type of a hard graphite. That's what you get, the structure that you can then put in electrodes and stuff. So it all depends on the high temperatures and the time that you spend in a reactor. Right? So, and what I'll show you is that what we work on mostly is a fast pyrolysis to maximize the oil, and the co-product that you get, a biochar, and normally is a short residence time. Right? So eventually you don't have structure, you don't have surface, and you still have some volatile in it. And when in that, you mix that with the soil, and then all the dynamics and stuff, the complex dynamics that start to take place. Right now, the biochar is something that is a religion, right? And so everybody preaching as to what it will do for you. But again, what we don't know is the soil people and what they need. But what we can produce for them to make their work easier. Okay. So today I will talk about our work here. Our co-authors will be Isabel Lima, who is at the Southern Regional Research Center, and also Tom Clayson. Sorry, excuse me. Oh, okay. And what we do here is a biomass show here. We do a pyrolysis, and this program comes under the pyrolysis or thermochemical conversion. We all know about talk a little about several pyrolysis pathways, conversion pathways, and you see the thermochemical is a major part. Most people know about biochemical conversion, but our interest is in fuels. So we focus on fast pyrolysis here for bio-oil. So we maximize our process for bio-oil production. But the co-product is a biochar. So, and our interest is to take it to soil, make it a soil amendment. We have a system here, as you see in the middle, that we take a biomass and take it through our system, a reactor, which I'll talk a little bit about, as they call the Quasinator. It's essentially a fluidized bed reactor, and we make a bio-oil. And the co-product is a biochar here. This is our reactor, and the front big part here is essentially control systems provided by our partners, Siemens. And we have a fluidized bed, char, and this is our char catch in here. So we get all our charcoal in here, and the vapors continue onwards here until we collect all the liquids that come out. So from the entrance of there's a back here has a feed hopper, which we crush or we mill the biomass into say 2-3 millimeters, because a fast pyrolysis particle size matters to get a high heat rate into that. To stay at the temperature, fast Pyro's temperature around 500. So with a small particle size, we can put in a heat about 1,000 degrees C per second. From entrance into the reactor to the exit, the total residence time is about 8 seconds. Within the reactor itself, it's about 0.1 second. And so you can imagine that there's not enough time to anything to really, the charcoal to really develop. And the slide here will show you what kind of yields we get. And we can get yields as much as far as 70% yield, and we've done several biomass, and we tend to want to group them under woods, grasses, and legumes and stuff. And I want to quickly talk about the legumes. If you know nitrogen cycles, if you talk about nitrogen fixation plants, and you add a biochar, what happens to it? But importantly, the green line here is the charcoal production. As you can see, we can get as high as somewhere around 40%, which obviously chicken litter got a lot of ash in that, to as low as somewhere around maybe 15% of the biochar, so very small. But with this process, what we do is we want to maximize the bio-oil, like I said. So the syngas is supposed to be for what we use to power the system. May not be enough because a little bit in here, but we have to use some of the charcoal to power the system. The remaining is supposed to be for soil. Okay, so that charcoal is very important, and we try to characterize it and find its suitability for soil use, or as fuel, or any other, or for that matter, metal absorption or soil conditioning remediation. So here, as you see the slide here, the total yield for different several biomass, and we can produce a char here with a moisture content in here. The bulk density is a very, very low, as you see here. So we characterize here that we look at ash content site. We do the particle size characterization, also pH, and we see the particle size here very small, some 300 to as high as 700 micron. So you once got to be very careful in terms of how to handle it, because it can get in your lungs. The pH, as you see here, is all range here around 7 to 8, as it looks like chicken litter, so very high pH compared to the bio-oil, which is about 2 pH, about 2. The ash content range, I'm surprised is that low, but soybean straw here is very low here, corn cob and alfalfa and the switchgrass and other stuff here. The surface area, someone mentioned, a question came up, and as you can see, the surface area here is for the charcoal is very, very low. What we do is we try to find value to this charcoal. So we look at it as after we produce a charcoal. So what do we do if we activate it? Right? So we activate the biochar in a stationary steam activation around a high temperature, around 700 degrees C. So you can see that the surface area then explodes from here, from around almost non-existent to the CATI showed around corn cob around 2-3, which is about the same that we got here. Some essentially got almost nothing, zero surface. But then when you steam activate it, you get surface areas, very high surface areas in here. All right, so the purpose is to find value if you can use it for soil can easily be used for as an activated charcoal. Look at here, I said for the char, the pore volume here is almost non-existent in most of them, but we start to develop pores and stuff in millipores in here. And the millipore areas is about from 192 somewhere to as high as about 7, close to 800 meters squared per gram. So this is what you see here. As you see the charcoal we produce or constover, and what we get when we activate it. So the surface areas actually explode, as you see the surfaces, the interfaces in this slide. But someone asks the question, does it matter if you really want to use this in the soil and stuff like that? So in the next slides, I will show you metal absorption for the carbons and also for that. But this slide here is a continuation of the other slides. I lumped all of them together. Here the SEMs of those, all the child that we have done in this study. So what we did here is we look at the absorption with and the biochars, as you see here, of copper, cadmium, nickel, and zinc. And we compare that with a commercial activated carbon in here. And you see that this really, the biochar, really does really well in absorption in 1 molar solution. So if you look at it here, I just wait a little bit for you to absorb it, a little bit, and if you go to the next here, this is for carbon, activated carbon. And you see that though some of them we have a very, very high percent absorption, they're essentially about the same. Not that very different. All right. So the question as to whether the surface area matters for metal absorption, it really doesn't. So the cation exchange is really not surface area dependent. So the biochar that we get from fast pyrolysis, those very low surface area, we don't need, if you put in a soil for soil remediation, it's still equally very good.
What's the unit?
It's a percent, actually, sorry about that.
Percent weight or?
Yeah, percent weight in the solution.
No, I don't think you're going to get 79% carbon. Is this all for the same concentration?
Yeah, for the same concentration. And I will show you in the next slide here, after the competition, if you put it into the solution together. Okay? So if you put in a solution together in competition, this is what you got. Okay. So essentially, what we do is we try to find value for the charcoal that we produce for soil conditioning, necessarily maybe for forage or yield or something, but also for soil conditioning.
That does not mean adjusted for ash content, right?
No, this is not adjusted for ash content. It's all contained, it's all whole ash. What we do is we take the biochar as we have it, when we produce it, complete production, and then we carry that into the next furnace and reactivate the surface, right, using steam activation. But the problem with the steam activation is the temperatures are very high. It's around 700, 800, even at times 900 degrees. So whether that is economical, the economics show that's one thing. But importantly, it will show that the surface areas that we all worry about, for when it comes to metal or soil conditioning, the surface area is not an issue. Like I mentioned before, my co-orders are these two. Most of the activation work was done at Southern Regional Research Center. Collaborators in my lab are these gentlemen. And I'll take any questions that you have on this or any other biochar or any other pyrolysis questions that you have.
I'm wondering what kind of concentrations you use for the adsorption tests, those cations, different.
Yeah, that was the 1 millimole, let's see, molar concentration.
Then you choose such a level of concentration.
No, we have tried with no reason. But that's a low concentration enough for I don't know what happened at a very high concentration. We have some study with the 1 and 5 millimole, but I don't have the data for that.
In general, once we have a high concentrations, we can always get more capacity.
That's possible.
Yeah, it's possible that at 1 millimolar, and you add it to something that's pH 7 for some of those heavy metals, it's more of a precipitation reaction rather than what you would call absorption or absorption.
It's more what? Excuse me.
Precipitation. I mean, you're just precipitating the metals out rather than doing a straight absorption. Well, do you know what the pH was when you did these absorption reactions?
The pH of the
When you put 1 millimolar copper and the biochar, what was the pH?
biochar.
What was the pH of the system?
I don't know, but the biochar pH of the biochar was listed as about 7, about almost neutral to 8. So I don't know the whole system pH. I can't tell.
Well, I think what Mike is saying is you may not have been getting absorption.
No, absorption of the metal.
Precipitation rather than absorption.
Absorption. Okay, I will check with my co-authors.
Another question? In the back? Well, first thank you in the back. and then-
Okay. My question is about the when you activate the charcoal. According to Hugh McLaughlin, I think many of you know him, the just pure activated charcoal is not desirable with regard to soils for the plants. And when you activate your chars, which have been produced by fast pyrolysis, are you creating a type of surface area adsorption capacity which has been shown to be useful for plants, or is it more in the category of the industrial activated charcoals and has other purposes?
That's the idea. The idea is the biochar we produce by fast pyrolysis, could it be used for soil amendment like a biochar for soils? It's not necessarily for industrial application. Can we add value? Because we have very short residence time, we want to, after that, condition the char. Like someone said, design a char or something to reduce the the oxygen content or somehow. And in the process, increase the surface area, for it to hopefully help the soil and plant dynamics, right? But we find out, we find out that for the carrion change, perhaps it doesn't really, surface area doesn't play so much role. And this study is collaborated with a study in Georgia, Mississippi State, in fact. But the purpose was for soil. So that's so that we can add structure to it before we put it into the soil.
And you say that it was accomplished and is successful? I mean, Dr. Spokas, you did field tests, I think, with the fast pyrolysis. I mean, anybody in the audience, is there somebody with information about the fast pyrolysis chars and their impact in terms of soil, as opposed to the slower pyrolysis or gasifier chars and their impact, both of which can have substantial surface areas?
Yeah, we haven't done what you call it, greenhouse studies to look at that. But from the studies that I see with the effect of, based on the volatile content, when you activate it, then you remove all the volatile, and give it a structure and surface area, which we're hoping that people are still working on studying soil and plant effect on that, but I don't have data for that. Yes, Katie.
One of the key arguments you mentioned about why activated carbon may not be used as biochar as often is the economic cost of that second step. Do you have an estimate of what kind of cost increases you're talking about? So rather than just doing pyrolysis and activation, what kind of cost differences would you expect to see?
Well, we did, I'm sorry I don't have the data right now, but we did some, Isabel did some work in the South with the chicken litter, where he did economic analysis of the whole thing. I can get the paper for you. Yeah, but in terms of as an added process to fast pyrolysis, obviously there will be a huge difference. If you're going from 500 degrees C to somewhere around 800 degrees C, the temperature difference of about 300 degrees, multiplied by the feed rate, the heat capacity, you're talking about huge energy consumption.
One more I forgot. Did you mention exactly which temperatures you were using in your activation? Was it?
So 800 degrees.
Was
C, yeah, C.
Take another one? Okay. In your slides, but also in other slides presented, we've had characterized the pyrolysis regime, slow and fast, and hydrothermal or the other, and then gasification. In the gasification realm, the typical gasifiers first conduct pyrolysis, and then they do char gasification, which has been the traditional thing for decades in that. Some gasifiers are able to do pyrolysis not totally independently, but you can get the char out before it goes through the very high temperatures typical of downdraft gasifiers, okay? And by pulling out those chars in it, so it's more of a comment that in these graphics, yours and in the other ones that have been shown, there's probably another category that isn't totally represented. They simply say all gasifiers are high temperatures, 700, 800, and that is not quite the same thing. So I just wanted to make that as a comment because it came up in your slides.
Yeah, that's true, obviously. There are different type of gasifiers, different type of temperatures, different type of residence times. So you're going to get and also different type kind of oxygen injection, right? So you're going to get some of the carbon burn off. It all depends if it's surface combustion or something, or gasification, what happens to the char structure. So they all got different type of carbon char structure and type, so to speak, including ash content. So they all play different dynamics in a soil.
Do you have any other questions?
Well, we at ARS Biochar Initiative, we have an agreement with I think two companies. Two officials. That's a Dynamotive and Best Energies. Best Energies will be a slow type pyrolysis. Dynamotive is the same as fast pyrolysis, like mine, but they are commercial, so they have a lot on place.
I'll just add a little bit to this. Within the ARS, we go through what's referred to as material transfer agreements, and I've entered into about 27 of these agreements total. 13 of the companies that I had agreements with 2 years ago no longer exist. There is a lot of economic reasons, and right now you kind of see the whole question of, after they get biochar, what are we going to price it at? Well, it's compared right now to a lot of the soil amendments. The problem is, we don't have any history. There's no way to guarantee that this is the response you're going to get. People call me weekly asking, well, how much should I apply to a field? I said, we don't have the data to even come up with a number yet. And it's very frustrating because there's so many people that want to use biochar, but we don't understand the fundamental soil reactions that are necessary before we extrapolate that out to application areas. So the question about where we can actually get biochar, there are sources out there, but there is really no, you can't go to Home Depot or Lowe's or any of the home improvement stores. There are a lot of entrepreneurs and a lot of companies out there that are currently selling biochar.
And some say it costs $200 a ton, and some say it costs whatever, ridiculous numbers. But I would say I always rate it at as a fuel. You know, if you look at the coal price, maybe you could sell at $30 a ton. Yeah.
What yield you can get from the biochar, the pyrolysis char to the activated carbon? Because during activation, some carbon will be chewed up.
Yeah, you get about 30%. About 30.
30%.
Total, yeah. So if you got a 70% or 60, normally you get pyrolysis, you get about 65, 60% is normal. It's possible you can get 70%. Then you activate it, you know, so you can get almost about half of that because you volatile most of it, and you want to wash, you know, so it's a kind of a low rate.
Just one more. In terms of your comment, the earlier comment about biochar for sequestration purposes as opposed to the soil, leaving the soil issue aside from it.
Yes.
In the fast pyrolysis chars, which have some volatiles in it, wouldn't they be of higher value, meaning greater amount of carbon atoms in it, than if you did activate it? If you were going to bury it, you should bury it just as char, not as activated. Not in soils, I say put it in an old mine shaft.
Well, again, we don't know. I mean, what happened, you know, if, but what I say, if you look at the graph that Kirk showed, when you have a graphite, you don't have any oxygen in it, perhaps you have a better chance. Eventually, everything goes down to this normal fixed carbon state, you know. So if you have a volatile in it, eventually, there will be some exchange, you know, just like you have your biomass, you know. Yeah, well, there's
part of the New Zealand standard for biochars, they actually included landfilling, of all things, for carbon sequestration. They looked at all the data and they said, that is the safest mechanism right now for carbon sequestration, is to put all this char into a landfill. It sent quivers up all the biochar supporting community, and I said, everyone should have supported that, because the sole thing, this biochar name, like I've been trying to emphasize, is carbon sequestration. Solar fertility amendments, that was all side effects that people have seen after the charcoals have been intermixed with the soil. But biochar as itself is solely should be focused on the carbon sequestration value. And whether that char ends up in a landfill, in forest soils, in wetlands, in agricultural soils, the carbon sequestration value is still there. The one facet of this is there's too much infighting in the biochar community, as you kind of see from all the questions and the answers of this. We have to get behind this. If we want this material to be accounted for in the carbon sequestration, we need a unified front. If we have all of this divisions within ourselves, imagine what the policy and the regulators are going to be looking at. They're going to be calling all the various scientists and saying, biochar stable in soil. They're going to get an entire range of responses.
But I think, Kirk, they also, because there's differences in results of, you know, in terms of its effect on plant growth and forage yield and all those kind of stuff. Because I've seen some biochar that they give naturally nothing, and some really. So it's up to the plant scientists and soil scientists really give a feedback as to what this is doing in terms of what type of plant. You know, for instance, legumes or something, they work well, right? Maybe it's because it has its own nitrogen fixation and stuff in there, but others may not work well, right? So we don't know all this, the final answer to that, right? How it relates to production. You know, like you got Jeff Novak trying to see designer char or something. He's looking at how the temperature effect on it. If you leave it a high temperature, longer time, and you cause it form some graphite, or which I don't think is graphite, but at least more stable, what it does to the soil or the plant, we don't still know. So it will take some time, maybe about 10 years or so before we really get answers. But right now, people are just jumping the gun and they're preaching, right? So what happened is I can sell you $200, $100, and all kinds of, and then they go out of business the next day.
We'll take a couple more questions. BK, if you don't mind.
What's the final yield of the activated char on the basis of biochar that you started? Is it 50%?
Yes, I say that eventually from plant, 50% of the biochar that you put in.
How is it on the basis of the biomass?
That's the biomass, about 60%, 65% of that. So 50%. That's what I said, or I tell you, I have calculations wrong.
This could be a question for anybody, really, but has there been any efforts to clean development mechanism yet? Is anybody aware of anything?
What?
The clean development mechanism under the FECC to look forward to doing that. I know Kurt and I have talked about this, as to whether there's progress toward this front.
You mean from remediation or what?
No. Well, it could be. I mean, it could be regarded as a clean development mechanism, but I'm just talking more about sequestration in general, be it soil carbon, be it sequestration of nitrous oxide, be it sequestration of carbon dioxide. I guess my question is there anybody, is the International Biochar Initiative doing anything yet that we know of? I mean,
yes, IBI is lobbying with what's referred to as the meth panels. Before a CDM protocol is adopted, it goes through an entire scientific process of a meth panel, which is a methodology panel, recommends a certain procedure for how you're going to document the actual tons of CO2 sequestered. The problem that biochar faces is the same as all soil carbon sequestration areas. The lack of an easily validatable methodology for measuring how much carbon is sequestered. So the CDM, it has a lot of methodologies, but one is a validator has to be able to go out and confirm that the number on the paper, if you're saying that this project is sequestering 10 tons of CO2, they have to be able to see how that 10 tons number comes from. The difficulty we have with the biochar is getting that number. If you look at soil carbon numbers, we have just natural variability in natural soils. So it really depends where that validator would take that soil sample, and you can come back and say, no, you don't even have half the carbon that you said you had originally. And things like that happen. The Chicago Climate Exchange has appreciated all the soil problems, and they said, well, okay, we're going to take all the literature that's out there and take the median value for the carbon sequestration number. That has a lot of ag people upset, has a lot of forest people upset, but unfortunately right now, what they're stuck with, that is a very solid way of doing it. And you can kind of see in the numbers that I had up there for the biochar, we have an entire spectrum. And if some people say, well, it's very degradable, others say, no, it's stable. Right now, the meth panel for biochar has looked at it, and they said, well, it's identical to the forest residues, to actual wind instability. That's going to be our next fight, to show that it is more stable than lignin.
A comment on that, one of the reasons I did the biodiversity study that I did is it would be very simple if you could drive your truck across the scale, the truck's full of biochar, and you know the properties of the biochar well enough that you can say, I'm throwing on 1 ton of biochar, but I know that 5% will disappear. 5% is available. Therefore, I can show that 95% of what I applied is staying there. That would be an ideal method, but the problem with even proposing that is we don't know how to estimate viability. We don't know how to estimate how long it's going to be. We make some pretty good guesses, but to me, that's what an ideal system would look like. If you know enough about the char you're putting down, you can put a value on it, even if that's just a fraction of whatever you're putting in the char.
So is it safe to say that USDA does not have a policy position on biochar?
Well, we don't have the maybe data, final data, but policy. I think our secretary is very much interested. You know he has a passion for the biochar. Yeah.
Well, that's the biggest benefit with being an ARS is within the research arm. We do not make, we do not draft. We only have the data as our.
So I think the question was that is there no policy position as that within USDA?
Currently, we do not have the data to formulate.